The key to answering question number 17 is understanding that you need to tilt the axis so that the x-axis is along the slope and the y-axis is coming out of the slope. In that case, the acceleration will be down the hill, and so we know that the net force will have to be down the hill as well. The key to answering question number 17, part A, is to realize that the axis should be tilted so that the x-axis is along the slope and the y-axis is normal to the slope. In that case, if you draw the free body diagram from a dot, gravity will always pull straight down. The normal force will always extend directly out of the hill, and friction will be up the hill. The free body diagram should only include forces that are real forces. However, to solve the problem, you'll need to break the force of gravity into its x and y components on this new tilted scale. So in our new system, the normal force is out of the hill, the friction force is up the hill, and gravity will be broken into two pieces. One piece that is into the hill, and another piece that is parallel to the hill, which we can move to make the picture look a little neater. A free body diagram should only include the forces that are real. So once you have those three forces, part A is done. Now to answer part B, we need to redraw the picture in a way that will be more helpful to us. So we'll have the normal force out of the hill, the friction force up the hill, and we're going to take gravity and break it into a component that is into the hill. We'll call that FGY, and a component that goes down the hill. And I'll redraw that up here and call that FGX. There are a few things we know about this picture. First of all, Fn and Fgy have to be equal to each other because there's no acceleration happening into or out of the hill. The question is, how do FF and FGX compare? And once we know that, we can figure out the acceleration. Using our previous picture, where the angle was given as 30 degrees, we can move back to our new drawing and transfer that angle to this spot right here. Now take a minute to see if you can convince yourself that that angle there is the same as the angle in the original drawing, 30 degrees. Coming back to our picture, we now need to figure out what these forces are, the friction force and the FGX. So let's fill out some information that we do know. We know that FGY is mg cosine 30. And we know that that is also the same as Fn. In addition, we know that the force of friction is mu times the normal force. In this case, friction is, the coefficient of friction is 0.1, and we know the normal force is mg cosine 30. The force in the x direction, that's this arrow here, which we've redrawn up to here, is opposite from the angle. So we know that fgx is mg sine theta, or theta being 30 in this case. Now to figure out acceleration, we're always going to use Newton's second law, which is acceleration is equal to the net force divided by the mass. In this case, we're just worried about acceleration in the x direction, so we need to know the net force in the x direction. That net force is going to be Fgx, the force down the hill, minus the friction force holding it back up the hill, and then divide by m. Now if we expand this, we know what that is, and we know what that is, so I'll use the space below to write that a little bit larger. We know that Fgx is mg sine theta. We know that Ff is mu mg cosine theta. And that is all divided by m. Now right away we can see that every part of this equation has an m in it, so we find that m does not matter. And we get that the acceleration down the hill is g sine theta minus mu g cosine theta, and then all that's left to do is plug our numbers in that were given. So this would end up being 9.8 times the sine of 30, which is 0.5, minus 0.1 times 9.8 times the cosine of 30, which is 0.866. And plugging those numbers in, we end up with 4.05 meters per second squared. Once we know the acceleration, it's an easy step to solving the velocity at the end of a time using a kinematics equation. We know we started from rest. Our acceleration was 4.05, and that happened for 4 seconds. So our final velocity will be 16.2 meters per second.